So my name is Erica Hammerstein. Until very recently, I was a graduate student at the University of Maryland. I defended, that's why I didn't get kicked out or anything. But so yeah, I was a graduate student at the University of Maryland, and I'm going to talk about population studies of tidal disruption events and their host galaxies, selected from the Optical with his Wiki Transient Facility. So I think we're all here because we love TDEs, and they're really great tools to study things like accretion disk formation, jet formation, and the phases of supermassive black hole accretion we don't normally get to see on such short timescales in things like AGN. They're also great ways to study the connections between supermassive black holes and their host galaxies, galaxy evolution, and just kind of the general dynamics of nuclear regions of galaxies. Now, the cool thing about TDEs is they can potentially provide independent measures of supermassive black hole masses from their light curves. And this is going to be crucial for future initiatives like Rubin, which are going to be discovering probably thousands of TDEs. Now, TDEs are preferentially going to happen around kind of lower mass supermassive black holes, and so they're really great ways to probe this lower mass supermassive black hole population, which is kind of more sparsely populated in relations such as M sigma here. So we just had a really great overview of kind of the issues or current questions we're facing in terms of optically selected TDEs. And the big one is that we don't have a great handle on where the optical emission is actually coming from. So we have the optical emission here is at a much lower temperature, much larger radius than the X-ray emission, which we think is probably coming from the disk. Of course, there, like we just learned, are several different models to explain where this emission could be coming from. And I won't go into detail since we just heard, but the cool thing about these models is that they kind of make different predictions for how the observed emission might depend on the properties of the black hole, which means that we can test these models by discovering and characterizing larger samples of TDEs in the black holes at the centers of them. So, in the past maybe decade or so, optically discovered TDEs have kind of really led the general TDE discoveries. Of course, back in the late 90s and early 2000s, we had primarily we first discovered TDEs as X-ray transients. But in the past several years, it's really been in the optical. And ZTF has kind of been leading a lot of these discoveries. So these are just the TDEs that I could find on in the literature from 1996 to 2023. ZTF was responsible for about 30 of those within just the past several years that ZTF has been running. And then there's, of course, been several new samples at other wavelengths as well in the radio, the infrared, which we're going to be hearing about later, further ZTF objects in the optical from Yuhan, and then in the X-ray as well. So what can we do with these samples of TDEs that we are discovering? My work focuses a lot on trying to understand kind of these three questions. So where the optical and UV emission is actually coming from. And then if we understand that question, we can hopefully start answering this question of whether or not we can use the light curves to probe the population of supermassive black holes and their properties. We just have to understand where this emission is coming from. And then lastly, what are the properties of TDE hosts, and what is that connection between these hosts and TDEs and the rates at which they happen? So I'm going to introduce the ZTF1 sample. So ZTF1 discovered 30 TDEs, which I'm showing here in their light curves. It was a range of different spectroscopic types, so TDE hydrogen, hydrogen plus helium, and then a new class that we dubbed TDE featureless, which I'll talk about in a moment. They cover a range of redshifts, a range of host galaxy stellar masses. Cool thing about this sample is that all of these objects have at least one epoch of swift UVOT and XRT coverage. Some of them even have pre-peak swift coverage as well as pre-peak optical spectra, which is not something we had a lot of before ZTF. And then with ZTF force photometry, we can actually get detections for a lot of these events out to maybe even greater than 3 years post-peak. Now, I'm highlighting these 4 objects at the top here. You'll notice that most of the events kind of peak somewhere around the -18 to -20 in absolute magnitude. These ones peak something more like -22 to -24. Now, these are those featureless events that I talked about. So throughout ZTF, we were discovering lots of new TDEs. Most of them looked like these ones on the right when we looked at their optical spectra. So most of them had either broad hydrogen, broad helium, or a combination of the two. But when we were discovering all these TDEs, we found these objects that looked pretty much identical to the rest of these in terms of their light curve. So they were nuclear, of course. They had blue colors, and they stayed blue. There was very little cooling in their light curves. And then they also had very similar rise and fade timescales to these other TDEs that showed broad lines in their spectra. The difference, though, is one, they were more luminous, and two, they had pretty much zero broad lines that we could see in the optical spectra. Some of them do have host galaxy absorption lines, which is how you kind of how we get the redshift. But yeah, they didn't have any sort of broad lines. They also didn't really show any evolution. So if you took a spectrum at earlier times, took a spectrum at later times, they were still pretty much featureless. They also have more massive and redder hosts compared to the other samples. So this is a color magnitude diagram. These featureless objects are up here on the right. This could be hinting at maybe the properties of the black hole at the center. There's also this possible similarity to jetted TDEs, which I'll talk about in a moment. So we can take all of those light curves and we can start looking for correlations between the timescales and things like the host galaxy stellar mass, which we have to use as generally a proxy for black hole mass, since we don't have actual black hole mass measurements for a lot of these events yet. So when we do that, we do find some significant correlations. So I'm showing here the decay timescale versus the host galaxy stellar mass, for which we find a significant correlation. And this has been found in other studies as well. So Schuart's studies, Yuhan also published the later ZTF sample, which found a similar correlation. So this is telling us that we can use these light curves to kind of probe the properties of the black holes. It's just a matter of actually figuring out the details there. Now, Muriel talked about kind of the differences between X-ray bright and sort of more X-ray faint events earlier today. And that's one thing we looked at in this sample as well. So we tried to compare the objects in our sample that had X-ray bright, or that were X-ray bright or X-ray detected versus the ones that were not. And when we look and we compare the host galaxy masses, which again we're kind of using as a proxy for black hole mass, we find no significant difference in the host galaxy mass between the X-ray bright and X-ray faint samples. Now I mentioned that the models for TDE emission kind of predict that the observed emission should sort of maybe depend on the black hole mass. And the fact that we're not really finding a difference between ones that show X-ray emission and don't show X-ray emission could be pointing towards a model which doesn't have a strong dependence on black hole mass. So that could be like the viewing angle model, for instance. Now I want to caution that these are all optically selected TDEs, so we have to look at TDEs kind of discovered at all wavelengths, showing all types of emission to really dig into this. Okay, so moving on to host galaxies. I'm showing here on the left the 30 TDE host galaxies from the ZTF1 sample, and they look kind of boring. I probably could not tell you the difference. If you showed me like this one and this one, I couldn't tell you which one was which. We usually find that most of these samples are kind of dominated by elliptical galaxies with very few spiral galaxies, save for the kind of lower redshift ones. Now I have asterisks here because at these higher redshifts and at these stellar masses, these galaxy stellar masses, it can be very hard to actually pick out any sort of features, especially with something like SDSS. But generally we find they look kind of elliptically. I think we're going to hear later on that maybe this isn't the case for samples studied or discovered at other wavelengths, but this is kind of the case in the optical. Now, when I look at TDE hosts, I generally like to compare them in 3 different properties. So that's their optical colors, their morphology, and their star formation history. We heard a little bit about this. So in terms of their optical colors, TDE hosts are green, so they live in the green valley, which is below the red sequence of kind of red passive galaxies, mostly your ellipticals, and above the blue cloud, which is blue star-forming galaxies, usually your spirals. And when we compare the number of TDE hosts to the general galaxy population that lives in the green valley, we find that 50%, usually 50% of TDE hosts live within these 2 dashed green lines, compared to about 13% of normal galaxies. So this is not insignificant, and it is pretty interesting. Now, when we look at the morphologies, which we can quantify using the Sersic index, which is just fitting a Sersic profile to the galaxy light profile, we find that TDE hosts are generally more centrally concentrated, 1, than galaxies of similar mass, and 2, if you look here on the right, I'm splitting up this background sample into kind of some interesting subpopulations. we find that the TDE hosts are generally more centrally concentrated than other Green Valley galaxies as well, which typically live down here with a Sirsic index of maybe about 1. Now moving on to the star formation histories. We kind of find, this was already pointed out, but TDE hosts, or samples of TDE hosts, are dominated by E plus A galaxies, or we find more E plus A's than we should in TDE host populations. Typically, this is about 10 to 33% of TDE hosts can be classified as E plus A, which live down here in this H alpha emission, H delta absorption plot. This is compared to only about 0.5% of the general galaxy population, kind of just depending on how you define E plus A. Now, this is all kind of coming together in a picture that likely supports the fact that mergers are responsible for this unique combination of properties. Now, mergers, of course, are going to change morphology of a galaxy. They're going to change the kinematics on multiple different spatial scales. And so we are interested in exploring that. And that's exactly what we've done. Now, IFU observations are a great way to explore things like this on multiple different spatial scales. So we got some KCWI observations of a subset of those 30 TDEs. These are those 13 objects that we observed. The KCWI field of view is the yellow box. And IFU data is really great because you can kind of investigate global properties of a galaxy, so the kinematics and the stellar populations. You can also extract things like bulge kinematics to get supermassive black hole masses. So this is what the KCWI data looks like. You have all of these bins, each corresponds to a spectrum. And then we can take these spectra, fit it with something like PPXF, and get out lots of lovely information like the line of sight velocity, velocity dispersion, and then properties of the stellar population. So when we look at the global kinematics of the TDE host galaxies, we might be interested in looking at kind of the level of rotational support that they have, because that's going to be linked to its merger and star formation history. We quantify this by something called V over sigma, and it's just the ratio of order to random motion in a galaxy. So a higher V over sigma means something's more rotationally supported. It's going to be something like a spiral galaxy. And a lower V over sigma is going to be more pressure supported or velocity dispersion supported, which is going to be more like your elliptical galaxies. There's also this correlation between the level of rotational support in a galaxy and the age of the stellar population. So the correlation is such that more pressure-supported galaxies are going to have a lower V over sigma, and they're going to have older stellar populations, and younger stellar populations are going to be more rotationally supported. They're going to have a higher V over sigma. And this is linked to a galaxy's merger and star formation history. So when we look at the TDE hosts and we start comparing them to interesting subpopulations, so again, I've split this background sample, which are these colored pixels, into some interesting subpopulations we might want to compare to, such as E plus A galaxies, which is the purple kind of dot dash line. We find that E plus A galaxies in this background sample are generally younger than the TDE hosts, despite having kind of a similar distribution in their level of rotational support. And I want to focus on these kind of, I don't know, 6 galaxies down here, 6 TDE hosts down here. So these are very likely more kind of like pressure-supported galaxies. But when we compare them to galaxies that have a similar level of rotational support, we find that the TDE hosts are, 1, significantly less massive and significantly younger than other galaxies with a similar V over sigma. So this could be telling us a few different things. Either the black hole mass in these galaxies here is too high to kind of produce an observable TDE flare, or something is happening in the nucleus of the galaxy to the properties that boost the TDE rates, and the factors that boost the TDE rates evolve independently of these large-scale galaxy properties. And this could be hinting at the reason why we don't see TDEs in these kind of older ellipticals despite having similar global properties. It can be very difficult, though, to actually connect these global properties to factors in the nucleus that are directly affecting the TDE rate. So we definitely need to do a little bit of more work there. So I mentioned we can also get the black hole mass from M sigma and the bulge kinematics, which is exactly what we've done. And so this is a black hole mass distribution for those 13 objects. Peaks around 10 to the 6, exactly what we expect. There is a lack of kind of higher mass black holes in the sample, which is, again, kind of what we expect. We find pretty good agreement with the host galaxy stellar mass, but I'm highlighting this one object because it is an outlier for a few different reasons. So this one is one of those featureless objects. Again, it also has a very high black hole mass. And this has also been observed in other studies which have obtained black hole masses. So Yuhan's paper earlier last year got a few more masses for other featureless events and found that they were generally pretty massive, or among the most massive ones in that sample. Now I want to come back to this possible connection to jetted TDEs. So 2 years ago, with the discovery of 22 CMC, it was pointed out that it showed featureless optical spectra. It was also pointed out that the thermal component in 22 CMC showed very similar properties to these TDE featureless events, primarily that they peaked at very similar luminosities. So this is the 22 CMC peak, and then the purple is other TDE featureless events in the ZTF sample. And Igor is going to talk more about 22 CMC later this week. So because 22 CMC has this really great optically bright component, we can start making comparisons between jetted TDEs and kind of the general non-jetted TDE population. So on the left here, I'm showing the spectra of 22 CMC from about a few days post-discovery to maybe, I don't know, less than 20 days post-discovery. You can see this clear evolution in the continuum from something that's pretty red to something that is very, very blue. These last few epochs of spectra show remarkable similarity to these TDE featureless events. They're all featureless. They all have a very steep blue continuum. But when we want to make comparisons using the light curve, we have to be a little bit careful. 22 CMC, of course, has this very early time light curve that is dominated by the non-thermal component from the jet interacting with the circumnuclear medium. And the late time is dominated by the black body component, which likely has a similar origin to non-jetted TDEs. But we can't just make direct comparisons. We actually have to be very careful in modeling this early time component if we want to compare it to thermal TDEs. So we see this evolution in the SED here, where the darker colors are earlier times. It's dominated by this non-thermal component, and then at maybe about 11 days post-peak, we get something that is mostly dominated by the thermal emission. So this is very preliminary. Once we do all of that fitting and account for the non-thermal component, we can look at comparing this thermal component of 22 CMC to the other TDEs, the non-jetted TDEs discovered by ZTF. We do find that 22 CMC is pretty consistent with these other featureless events, which are the black diamonds. I'm showing the temperature and the luminosity here. So this is the luminosity and the temperature as a function of black hole mass. This is, of course, comparing one object to 4 objects. So the statistics here is not very robust. And there's plenty more that we can do to actually kind of explore this connection further. So, for instance, if the TDE featureless objects represent the off-axis jetted scenario, we might expect to see some late-time radio emission. So that's definitely something we could do. Of course, it's also possible that the similarities that we see here are not related to the jet at all. It could be related to something else. So for that reason, I'm really interested in exploring kind of the reason for this featureless spectra in these objects. So it could be something related to outflows, something else. I'd love to hear ideas. Lastly, I want to point out that this is an upper limit on the host galaxy mass. We actually don't have a good estimate of the host galaxy or the black hole. So once we get that, this could very well change. So I think I'm probably out of time. I will leave up some conclusions here and answers and future work, and I'm happy to take questions. Thank you.
Okay, thank you, Erica. Questions?
Thanks for the great talk. If you're suggesting this connection between the TDE featureless class and the jetted TDEs, we heard earlier that there's a suggestion that some of the jetted TDEs perhaps prefer less massive supermassive black holes. Can you comment on that kind of little bit of a tension there?
Yeah. So I guess I'll just go back. Yeah, so that is certainly a point of tension, that the featureless, the jetted TDEs kind of are maybe more consistent with having lower black hole masses, and these ones have pretty high black hole masses. So The one thing that we might want to look at is maybe that the reason that they are similar, one, this is the thermal emission. It's not coming from a jet or anything like that. So that is one thing to keep in mind. But one thing we might want to look at is why these things actually have featureless spectra. So maybe the reasons that they're similar aren't related to the jet. It's related to something more like, I don't know, some sort of other outflow or whatever is causing these objects to have featureless spectra. Could be the reason why it's the same in 22 CMC, but these are not necessarily jetted TDEs.
Okay. Another question? You were first, I think.
Cheers. Can you comment on the Eddington ratios of the featureless TDEs and how they compare to the Eddington ratios or a potential anticorrelation of Eddington ratio and black hole mass?
Yes, let me see. I believe I have.
Yeah, I thought you might have a slide on it.
I do, yeah, I do have the Eddington ratios somewhere here. I can't. Okay, here it is.
Nice.
Yeah, so sorry, can you repeat your question?
Sorry.
Oh goodness, that is not what I wanted to do. Let's bring that back. Okay, there we go.
Right. So yeah, I was wondering, so I guess there's one there, but how do you feel that the Eddington ratios of the featureless TDEs more broadly compare with that anticorrelation between Eddington ratio and black hole mass?
Yeah, so these guys are going to be significantly more sub-Eddington than these other ones. I will say that the uncertainty here is rather large, so if you were down here, it would be a lot more consistent. I think the real problem here is that we have one. So getting more would be really, really great.
Yeah.
Okay, that side.
So I have a question about the TD features that had a mass estimate of 10 to the 8 solar mass of the black hole. So does that large mass constrain the spin of the black hole to be very large so that it doesn't get disrupted out inside the ISO?
Yes, so you can do a little bit of investigation into that. So the mass here is, I think it's like 10 to the 8.01. So you could, assuming that that is the mass, you could put an estimate on the spin. When we do that, we get about like 0.16. I will caution, though, that the uncertainties here, again, are pretty large. And so if you're at the bottom of this range, it might not necessitate that whatsoever. Yeah.
Okay, I thought it might be related to the jet, but maybe not. Thanks.
Okay, let's go to this side.
Oh, yeah. So my question is related to the featureless TDEs. Are they all overly luminous, -22, or I thought Yuhan had a low luminosity featureless case. Is that still the case, or do we believe all featureless ones are overly bright?
To my knowledge, I think they're all overly bright. I don't know, Yuhan, if you had a comment on that.
I think it's only in 21 EHB that we have subluminous and featureless, and that one is also a European of other wavelengths. So I think the featureless class, most of them should be overluminous, and 21 EHB might be just an outlier.
I mean, it's an event. You cannot just ignore that.
Yeah, but that one also has thick transition in the X-ray that you also don't see in other wavelengths, and also very hard corona formation. So it seems to be very unusual.
Yeah, that one is very different in terms of the multi-wavelength. Like for most of these featureless ones, I mean, we don't really see, I don't believe we see X-ray emission really from those ones.
So you mean the theorists should really go ahead and make a model for the brightest ones, and then they are featureless, right?
Yeah.
Would you? Thank you.
Okay.
My question is also related to the featureless TDs. I think it seems rare, right?
Rare, yeah. So there are, among the 30 from ZTF, only about 4 of them are featureless.
And can you estimate the event rate of featureless TDs?
We have not done that. I don't know, Yuhan, maybe did you do that in your sample paper from ZTF 2?
Yeah, so they mostly have peak luminosity about -21, and it's the optical luminosity is a broken power law, so you can just integrate above -21.
I guess maybe the underlying question is that if, we have some estimates of the rate of jetted TDs, and I guess the question is, are they really, are the two consistent within the error bars when you correct for viewing angle effects and from the high energy selected events. And I'm guessing that probably still the ones that are jetted are still rarer because they were just such a rare. I mean, when I say jetted, the bona fide confirmed ones. But anyways, I think maybe that's an interesting question.
Yeah, no, that's definitely something we should talk more about. Yeah.
Okay, any other questions? We still have 5 minutes for discussion. If not, then let's thank Erica again.
Maybe one more question.
Oh, sorry. No, wait. There's another question.
Sorry.
Okay, no worries.
For the 3 features that you talked about, the Green Valley, the more centrally concentrated,
Yeah.
and the post-starburst E+A nature,
Yeah.
can we say anything about the sort of the time scale, like post-merger, that these TDE hosts tend to be in?
Yeah, you certainly could. So from, maybe not from this alone, but if you get a decent follow-up host galaxy, like spectra, for example, you can kind of look at, you can look at the ages of the stellar populations in the galaxies, how like post-merger they are, like when, estimating actually when the merger happened is a little bit more difficult. But you could certainly try and do that with like follow-up host observations.
Thank you.
Okay, going once, going twice. Then let's thank Erica again.